In this video, we are going to go over acids and bases equilibria. Equilibria is just another word for equilibrium. Let's first understand what makes a substance be called an acid versus what makes a substance be called a base. Acids and bases have particular characteristics. When it comes to acids, they turn blue litmus paper red. Litmus paper is an indicator that is utilized in the laboratory to look at acids and bases. In particular, blue litmus paper is the one that it is utilized for acids. And because this indicator can turn color into red, that's how we know that we have an acid. Acids tend to taste sour. Acids additionally tends to corrode metals. And one of the properties of acids is that they are going to be having or they can produce positively charged hydrogen ions. These positively charged hydrogen ions is what we call in chemistry protons. On the other hand, when we have bases, they turn red litmus paper blue. Bases tend to taste bitter. They mostly, in the majority of them that are known to date, are going to have negatively charged hydroxide ions. But in a few moments, I'm going to explain that not all bases are going to have OH, but many of them do. Bases to touch feel slippery. In general, most hand soaps and drain cleaners are bases. And strong bases specifically are going to be caustic, meaning that they irritate skin. When it comes to categorizing acids and bases, there are different theories that are going to explain how we can categorize a substance as an acid or as a base. The original theory that was utilized in order to categorize acids and bases came from the scientist Arrhenius. And in the Arrhenius theory, acids were defined as substances that contain hydrogen, while bases were substances that contain hydroxyl groups. So, based on this definition, they were specifically considering that HCl was an acid and that NaOH was a base. Later, they were able to observe that some molecules that do contain hydrogen not necessarily were acids. So the theory for defining acids and bases needed to be redefined. That's when Bronsted and Lowry decided to define acids as molecules or substances that are going to be proton donors. Remember that a proton is going to be a hydrogen that is positively charged. Bronsted and Lowry also created a definition for bases. They define bases as a substance that is going to accept a proton. We're going to see later how ammonia in water can be considered specifically either acids or bases in a system. There is one more theory for acids and bases, and that is the Lewis theory for acids and bases. Even though Lewis is saying things similar to Arrhenius and Bronsted-Lowry, the Lewis theory for acids and bases is focusing specifically on electron pairs. Acids are known as electron pair acceptors, while bases are electron pair donors. Out of the three theories, the one that is most commonly utilized and we're going to focus on is the Bronsted-Lowry. Acids and bases have different strengths. And understand that it is important that you memorize what are the 6 strong acids. Because things that are not part of these 6 strong acids, then they are considered weak acids. The six strong acids are HI, HBr, HClO4, HCl, H2SO4, and HNO3. You can see their names on the left side to the chemical formula. If an acid, it is not part of those top six strong acids, which are the only acids that are considered strong, then they are considered weak acids. And in the bottom part of this table, we can see some examples of weak acids. On the other hand, strong bases are defined by compounds that are formed from cations that come from group 1A, except hydrogen, and group 2A in the periodic table. Those cations that come from 1A and 2A, understand that when they're paired with hydroxides, that is what is called a strong base. Let's now continue our discussion of acids and bases in terms of Bronsted-Lowry acids and bases. As I just introduced to you guys, Bronsted-Lowry definitions for acids and bases define that an acid is going to be a substance that gives away an H plus, while a Bronsted-Lowry base is going to be a substance that accepts that H plus. Let's look at a reaction where this exchange of protons occurs. In the reaction that we have in figure 7.13, we can observe that we have a strong acid, HCl. And when HCl encounters water, when we look at the product of the reaction, we can see how H2O actually accepted a proton and it went from H2O to H3O. The formal charge of H3O is going to be positive 1. But in a way that makes sense because you are accepting a hydrogen that is positive 1. So since water is neutral, if you're accepting a hydrogen that is positive, that's why the formal charge is changing. Since water accepted the proton, that's why water is categorized as a base in this reaction. Since HCl went from HCl to Cl minus, this says that HCl acted as an acid because we can see that in the product side of the reaction, it's going to be just Cl. Now, this Cl is going to have a formal charge of negative 1. Because remember that in this process, the transfer is specifically an H plus. So if your molecule starts at neutral and it loses an H plus, then what remains with the molecule is gaining a negative charge. And in this molecule, because it started as neutral and it lost that H plus, then the remaining atom is going to be negative 1 charge. In this case, HCl is acting as an acid because it donated the proton to the water. In the reactant side of the reaction, we can only categorize our substances as either acids or bases, depending on the behavior that we see when we look specifically at the product. We also have names for the products that form in an acid-base reaction. So the substance that forms from the base accepting a proton, that is called a conjugate acid. While the substance that forms when the acid loses a proton, that is known as a conjugate base. Let's look at the following examples and let's define in these reactions that you can see are going to be equilibrium reactions because we have arrows in the forward and reverse direction. Let's categorize which substance is acting as an acid, which substance is acting as a base, and in the product side, what is our conjugate acid and what is our conjugate base. I'm going to do letter A and letter B. So when we look at this reaction specifically, we can observe how HNO3 overall forms NO3 negative 1. That means that in the process of this reaction occurring, there is a loss of H plus because HNO3 had a hydrogen in the reactant and then in the product it lost it. That means that in this reaction, HNO3 is acting as an acid. On the other hand, if we look closely at what's happening to the water accepted the proton lost by HNO3 and it became itself H3O plus. So this means that in this instance, water specifically is acting as a base. When it comes to the products of the reactions, remember that the substance that is produced in the product from the acid, that is known as the conjugate base, and the substance that is produced from the base accepting the proton is known as conjugate acid. Let's look at example B. Here we have ammonia reacting with water. We can see in the product of the reaction that ammonia changed from NH3 to NH4. So that means that ammonia accepted a proton. So in this example, ammonia is acting as a base, and then NH4 plus is going to be the conjugate acid for ammonia. We can observe that water had two hydrogens, and now in the product, it only has one. That means that in this reaction, water acted as an acid. And OH minus is going to be specifically the conjugate base so CO and J is my shorthand for conjugate. So OH minus is the conjugate base for water. Now we're going to learn how to name acids, starting with binary acids. When it comes to binary acids, these are going to be acids that are composed from mixing essentially H plus and a nonmetal. Notice that the nonmetals that we are going to have the formation of these binary acids are going to be the nonmetals that live in group 6A and groups 7A. The nonmetals that live in 5A, meaning nitrogen and phosphorus, actually make weak bases. I will show you after I finish naming acids, what are the chemical formulas in the name for those weak bases. But now let's focus on naming binary acids. So when it comes to naming binary acids, since we are going to start with hydrogen, then the name of a binary acid is going to start with the word hydro. Then, for the nonmetal name, we're going to use the stem of nonmetal name and then instead of using an IDE ending, we're going to replace it with the suffix ic acid. Let's do some examples. The 6 binary acids that you guys need to be familiar with are written in the bottom of the slide. Let's start with H2S. The name of that binary acid is hydro sulfuric acid. H2SE, hydrosilinic acid. HF, hydrofluoric acid. HBr, hydrobromic, BROMIC acid. HCl is hydrochloric acid. And lastly, HI, this is hydroiodic acid. As I mentioned a few moments ago, and let me just write it in a different color. When H plus is combined with nitrogen, that forms NH3. That is ammonia with double M. That is a weak base. When H plus combines with phosphorus anion, so phosphide, that makes PH3. That's phosphine. And phosphine is also a weak base. Let's now proceed to learn how to name the other class of acids. Now we're going to learn how to name oxyacids. Oxyacids come from the combination of H plus and a polyatomic anion. When we have oxyacids and we have to write their names, understand that the word hydro is not utilized. What we need to pay attention is to the ending of the name in the polyatomic anion. So if the polyatomic anion ends in ATE, that suffix is removed and replaced by ic, and then the word acid is added. On the other hand, if the polyatomic ion ends in the ending ITE, then the ITE is removed and is replaced by O's. And then you write the word acid. Be careful whenever you have polyatomic ions that contain sulfur and phosphorus, because the stem for sulfur, it's actually the word sulfur. So for sulfate, for example, which the chemical formula of the acid that comes from sulfate is H2SO4, the name for this oxyacid is going to be sulfuric acid. Because remember that this came from H plus combining with SO4 minus 2, and the name of this is sulfate. Let me give you an example of an acid that ends in 8, and we just add the ic acid. If you have, for example, the acid that comes from H plus combining with CO3 minus 2, which this is carbonate. The chemical formula of this acid is H2CO3. In its name, we remove the 8 and we put ic acid. This is going to be carbonic acid. Let's say that we have specifically the acid that comes from chlorite. So we have H plus combining with ClO2 minus 1. Chemical formula of this oxyacid is going to be HClO2. And the name of this oxyacid will be chlorous acid.